All right, and we're recording. Hey, physics class. Good to see you, I guess. Starting a new chapter now, starting with work, power, and simple machines. This will be the last chapter we get through. And just a pretty simple topic today, just the idea of what makes something work. And typically we use the term work incorrectly in our common everyday use of the word as opposed to how we would use it in physics. So work mathematically is equal to any force times a distance. So work is F times D, and this gives us a new unit. Work is measured in joules, and that's the same thing as a Newton meter. So essentially what this means is if you want to do work on something, say an Iron Man bobblehead, the force and the direction of motion have to be in the same way. So, for example, when I'm picking up bobblehead Iron Man, I'm applying an upward force and he's moving upward. Therefore, I've done work equal to the amount of force it took to lift him up and the distance he moved. If I'm setting Iron Man back down, that's when it gets a little trickier. I am opposing the force of motion, which is caused by gravity. I'm not doing the work. Because when I give an upward force and the direction of motion is downward, that doesn't mathematically work out. Or you could say I'm doing negative work because I'm actually opposing the motion of the object. So this does make it a little strange sometimes to realize that work is a vector problem, and what we would consider work or doing work commonly doesn't work that way. Made my own pun. Doesn't work in physics that way. So this is important to remember that it is a vector problem. Let's see, what else I want to talk about. Talked about that. Oh, and then of course angle matters as well. Sorry, so if you're pushing something at an angle, you have to take into account the percentage of the work that's actually going to move the object. I'll do an example problem. Hopefully that'll make more sense. So let's look at a couple pretty basic formula. Work is force times distance. Let's look at a couple example problems I worked up here. Just threw them off an old worksheet. So example problem number 1, after scoring a touchdown, we have this 84-kilogram receiver celebrates by leaping 120 centimeters in the air. How much work was done in the celebration? Okay, so again, of course, work is force times distance. You may be saying to yourself, well, wouldn't it make a difference if he is doing other jumpings or something? Yeah. If he jumped higher, he'd do more work. But his jumping is dependent on the force he exerts, right? So, really what's going on here, right? We have our receiver, and he is jumping and exerting a force, propelling him upward, and the height is 120 centimeters. And of course, we'll have to figure out the force required him to propel him and then the distance he travels. So his mass was 84 kilograms. The distance he travels is 120 centimeters. Of course, that's not a standard unit, so those of you who forget to convert from standard units, this is important. Changing that to meters would be 1.2. I can do this. I teach science. 1.2 meters. And then now the question is, how much force did he actually exert? Well, that brings us back to what is force, right? Force is mass times acceleration, and we know he's overcoming the force of gravity. So his force is literally just his mass times his acceleration. In this case, the acceleration is 9.8 meters per second squared because that is gravity. So 84 kilograms times 9.8 meters per second. And that'll give us his force. Then we add that in there times his distance, 1.2 meters. And the rest is calculator monkey work. 84 times 9.8 times 1.2, and I get a grand total of 987.84, which 2 significant digits, 990 joules. All right, let's continue with the second example problem. Here we have a tug of war. Team A does 220 times 10 to the 5th joules of work, pulling on Team B for 8 meters. What force was Team A exerting? And again, you may be saying to yourself, well, it matters how fast they pull. No, it doesn't, not according to physics. How fast they pull depends on power, but that's not the same as the actual amount of work done according to physics. All it is force times distance. So again, this one, relatively simple one. They give us the amount of work done this time, actually. Scientific notation there, 2.2 times 10 to the 5th joules. And it gives us the distance of 8 meters. Work is equal to force times distance, and it's asking us for our unknown force. So 2.2 times 10 to the 5th joules equals 8 meters times force. And again, we're back to calculator work. And I get a force of 27,500. Or if you prefer, 2.57 times 10 to the 1, 2, 3, 4th newtons. All right, so again, hopefully no problem there. One more. All right, on to the last example or problem for today. A lawnmower is pushed with a force of 88 newtons along a handle that makes an angle of 41 degrees with the horizontal. How much work is done when pushing the mower 1.2 kilometers through the yard? All right, so this, again, first blush, looks pretty simple. We have a distance of 1.2 kilometers, which would be standard units, 1,200 meters. Okay, and then the force of 88 newtons. But here's the deal. You're pushing on the lawnmower at an angle. So if we sketch this out, right, we have a, let me find my ruler here quick. All right, so if we sketch this out, right, draw a horizontal line. And when they're pushing on the lawnmower, it's at an angle of 41 degrees from the horizontal, or with the horizontal. So there's 41 degrees. So the angle is pushing in something like this, acting on, our little lawnmower. So the problem we have is that not all of the force going on the lawnmower is actually acting in the direction of motion. Some of it is acting straight down on the lawnmower, some of it is acting horizontally. So we can do our, thanks to the magics of geometry, take this force and resolve it into perpendicular and parallel components. So if this whole force is 88 newtons, we're really just concerned with the horizontal component of the force, and that, of course, is a trig function, right? This is the hypotenuse. This would be the adjacent side. SOHCAHTOA tells us that's cosine. So cosine of the angle times the hypotenuse, 88, and that will equal the horizontal component. Let's call that F sub h for right now, the horizontal component of the force. And that's what we have to use to calculate the amount of work done, because that's the only work actually that's the only force going into actually moving the lawnmower. The other force is pushing the lawnmower into the ground. Doesn't really help us in this case. So again, calculating that out, we have a force times a distance. So we go cosine of 41 times 88. And then multiply that by our distance, 1,200 meters. And I get a grand total of 79,697.33 significant digits, 3 significant digits. So that would be Well, 797 joules, or if you prefer scientific notation, 7.97 times 10 to the 1, 2, 3, fourth joules. So again, just some stuff to watch out for. Make sure you take into account angle whenever it's appropriate. I'll post your assignment on Classroom page. If you have any questions, get a hold of me, let me know. Otherwise, have a good day.